Let's go ahead and start with problem number 1. Number 1 says that people enter a line for an escalator at a rate modeled by the function r, given by r of t equals 44 times t over 100 cubed times 1 minus t over 300 to the 7th for values of t between 0 and 300 inclusive, and 0 for t is greater than 300, where r of t is measured in people per second and t is measured in seconds. As people get on the escalator, they exit the line at a constant rate of 0.7 persons per second. There are 20 people in line at t equals 0, and part A starts with how many people enter the line for the escalator during the time interval 0 less than t less than 300. So keep in mind that this is a rate, which means if I want to know the number of people, then what I'm going to have to do is take the integral from 0 to 300 of this function, r of t dt. So I'm going to have to take the integral from 0 to 300 of 44 times t over 100 cubed times 1 minus t over 300 to the 7th dt. So we're going to go ahead and do this. So I'm going to do F3 for calculator. We're going to integrate, and I want to integrate 44 times t divided by 100, I need parentheses there, raised to the third times, and open parentheses again, 1 minus t over 300, close to the 7th power. So that's my function. I want to integrate with respect to t from 0 to 300 and figure out what the result of that is. And we get 270. So this is 270 people that have gotten in line. These are 270 people that are getting into line for this escalator over this first 5-minute period, the 300 seconds. For part B, it says during the time interval 0 less than t less than 300, there are always people in line for the escalator. How many people are in line at time t equals 300? Well, keep in mind that I've got r of t, which is defined piecewise. That's at 44 times fractions. And keep in mind that this is on, but I also have people getting off the line, and this is also a rate. And that rate is a constant 0.7. So if I want to figure out the total people on, or the total people in line, I should say, that's going to be equal to the integral of the rate coming in minus the rate coming out. And again, I'm integrating from 0 to 300. So when I do this calculation, I'm going to go do my exact same equation. The only thing that's going to be different is my function's going to have a minus 0.7 in it. And now when I try and do that integral, I end up with 60 people. Okay, so the total people in minus the total people out over that time, because these are rates. For part C, it says for t greater than 300, what's the first time t that there are no people in line for the escalator? So for t greater than 300, r of t is 0, and s of t is still 0.7. So I want to integrate from 300 to some unknown t value, and I want to integrate 0 minus 0.7 dt. Well, this is going to be 0.7 t, which I'm evaluating from 300 to t, and I want to know when this result is going to use up all of these 60 people that we had in line. So I want to know when this is equal to 60. So I've got 0.7 t minus 300 times 0.7, and I want to know when that's equal to 60. And of course, I don't trust myself to try and, I don't want to factor, I want to solve. I don't trust myself to do this in my head or even do it on paper. I'm going to solve 0.7 t minus 300 times 0.7 equals 60, and I want to solve for t. And when I do that, I end up with t equals 385.714 seconds. So that's going to be the time that there's now no one on the escalator. It just takes 85 seconds for everyone to clear that off. Okay, on to part D. On part D, it says for 0 less than or equal to t less than or equal to 300, at what time t is the number of people in line a minimum? And it says to the nearest whole number, find the number of people in line at the time, justify your answer. Keep in mind that we know extrema occur at critical points and boundary points. And I know that my boundary points are going to be at 0 and at 300, so these are values that I'm going to have to determine. But then I also need to know extrema. And extrema occur when the derivative is equal to 0 or undefined. So for us, our derivative function is really that r of t minus s of t that we were dealing with earlier. So it's going to be that 44 times t over 100 cubed times 1 minus t over 300 to the seventh minus 0.7. And I want to know when this is equal to 0, and I don't have to worry about undefined because we're not dealing with fractions here. So we're going to go ahead and type this in. We're going to do another solve. And we're going to solve for 44 times t over 100 cubed times 1 minus t over 300 raised to the 7th. And that's going to be minus 0.7. And I want to solve this for t. Now I will tell you that this will take a bit of time. Wait, what's wrong with this? First argument of a solve or c-solve must be an equation or inequality. I forgot the equals 0. I need to take care of that real quick. Equals 0, because I'm looking for a critical point. Now, by the way, we've already done these answers over here, because here I'm doing the integral from 0 to 0 for this. And keep in mind that the initial people in line was 20 people. And I've already done the integral from 0 to 300 because that was part B. And on part B, that was 60 people. So I know that the number of people at time 0 is 20 people. I know that the number of people at time 300 is 60 people. So all I need to do is figure out the critical points of this expression. And of course, it is still calculating. It will take a while to do that, and that's okay. I've already done this, though, and I'm going to tell you that they occur at 33.0133 seconds, and t equals 166.575 seconds. Oh, look, it's already got that up. Great. So now what I need to do is I need to figure out what n of 33.0133 is, and what n, the number of people at 166.575. And that means I need to evaluate these integrals again. So let me see if I can go up to the integral that I had up here and just change the limit, because I only want to, in this case, I only want to go up to 33.0133. What did I do wrong with this? Syntax. I'm integrating with respect to t from 0 to 33.0133. I think I've got too many parentheses here. That's what it is. And we end up with negative 16.1966 people. Now, this has a meaning to us in the context of the problem. How can I have negative 16 people? Well, it must mean that the rate of people coming off the elevator was faster than the rate of people coming on, and at some point the elevator was empty. So this is really going to be 0 people. I'm going to need to do the exact same thing with 166.575. And this is 138.07. So in other words, this ends up being my minimum. And so I have a minimum of 0 people at t equals 33.0133 seconds. Now, it didn't ask where the maximum was, but my maximum is occurring at 166.575. And of course, these 20 and 60, those are just boundary points. So those are values in between. What's interesting to note is that this function looks an awful lot like a logistic function where I've got a constant times some population times 1 minus my population. And so I can imagine my population being this t over 300. So I'm expecting a curve that's going to do something like this. My rate's going to start off pretty low, and then it's going to come out high, and then it's going to flatten off again. And no coincidence, that just happens to look like an escalator. So that's problem number 1.